I bring you our exhaust-driven turbine. My name's Angel, we have Brian, and Efron. So, basic idea of our invention, per se, is introducing a turbine fan into an exhaust pipe of car or truck in order to generate electricity. That's our main big picture. So how it works, we want to get the exhaust air from the pipe in order to generate electricity. And this was our initial idea. So motivation. Our motivation is tied into reducing oil consumption. The idea behind this is to incorporate into more hybrid cars in order a way to generate electricity, in order to recharge the battery packs that they're using. That will reduce the consumption of oil, also preservation of the environment. And we'll utilize the wasted energy, like I mentioned before, in order to turn the turbine to generate electricity, and then increase the overall efficiency of the cars that exist today. So, oil is obviously a big, dirty mess. It has a huge global environmental impact. Right here, you have offshore drilling plants. All these leaks are causing damage to the wildlife, to the oceans, and eventually that's going to run out. Also, you have environmental destruction from oil. A lot of areas that are damaged like this, damage to soil. And not only does it damage the soil, but it has an effect on human life. So this is an example of oil conflict areas in Africa. Oil companies are going elsewhere. They're not staying here in the U.S. in order to get their oil. So how does that affect them globally? What damages their water supply, obviously affecting their lives. And a lot of these conflict areas use a military force in order to move people from where they're located, also causing lives just to get oil. So once, let's say we completely diminish their resources, that's eventually going to start ending up here, drilling offshore around the United States. Which is definitely not a good idea. Example would be the BP oil spill. Global market, we decided as far as global market to go with trucks for our pipe size. Since 1999, the hybrid engines and the cars have been steadily increasing for the past 15, 20 years. There's not really any development into trucks. Now trucks, they transport all your goods into all your stores, and they consume a lot of oil. You have huge trucks, you have what we call the earth movers, and then you have the conventional 5-liter trucks that you see in the streets. As far as fabrication, 3D printing, which everybody uses now, it's a big thing. We were able to go through a transition of different designs and blades in order to optimize what we came up with our end product. Apparatus. We used a multi-speed fan that we have here in the Transport Phenomenon Lab in order to best replicate the airflow that comes out of the car. We also use bearings, the PO2, and PVC pipes, also along with lubrication, meters, multimeter, and copper coils. Challenges of maintaining positive efficiency, have minimal induction of back pressure, so obviously we're introducing something into the car. We don't want that to affect the engine, because then it wouldn't be worth doing. So a good goal for us was try to reduce the back pressure by less than 10%. Also have a size limitation of pipes. These pipes that you see here are very small, so we couldn't really get our hands into it and fabricate inside, so we had to design an alternate way in order to be able to work with something this small or the truck size for our design project. And the big key, how do we generate electricity? Right? That's our added value. Also, before we go on, for our other testing, we couldn't really, within the lab, test in high temperatures, which is the consideration that we had. Pipes towards the end of the car or truck generally are 200, 250 degrees Celsius. closer to the engine, it's a lot higher. So that's not something we want to test and get burned. Not safe. Also, the carbon monoxide that's released by the gas, that's also not very safe for us to be able to test. So we tested in ambient temperature for all our results that we're getting.
And for our initial conceptual designs, we intended on having a turbine within the direction of flow of the exhaust gases on an axis mounted inside of the pipe. So as you can see in the first picture, the blades are mounted to the internal structure. And this caused a problem in terms of transferring power outside to generator, battery, however we want to transmit it. Our first design, we had a large focus on the area of reduction of the blades. So obviously a large center section of free-flowing gas would induce the least amount of back pressure. So that was our main focus. Because the turbine will be placed outside of the bearing itself, which is around the pipe, we need to focus on reduction of the area from the pipe, not necessarily from the turbine, which is why we have the turbine here with large blades. Here we see the screenshot of the cross section of the blades. The one on the left, we have about a 25 to 30% area of reduction of the turbine itself. The blade on the right, we see a larger area of reduction. However, this reduction is roughly 25 to 30% of the entering exhaust pipe area.
Another of the main challenges, as mentioned earlier, when it comes to being able to fulfill our designs or our goals of generating power, was be able to transfer that power that the blades were producing out of the flow area. Originally, from our proposed design as seen in the diagram, we were planning to use a central shaft that could be extended outward in order to be connected mechanically to a alternator or electric motor generator somehow. And we then decided to, in order to avoid any type of mechanical losses or energy loss into connections of using bevel gears or running connections of some sort like that, we decided to go with a more unique approach and be able to, in a sense, copy the principles that an electric motor would typically run on, is transferring power through magnetic induction. And the idea behind it is following the principles of Faraday's law. We decided to use coils and magnets in a set of a matter in close proximity to where magnets will be attached to the outside of the spinning duct or cylinder and be able to be rotated closely to the coils in which will be generating power. In the diagram there, you can see as in a typical magnetic induction, a magnet as is brought closer towards or away from a coil would be able to cause an electric current in one direction or the other, respectively. For our application, we decided to go in a more crossing the area of the coil, which occurred in preliminary testing, still caused the same amount of power as it comes towards the coil. It produces a forward motion of the current, and then as it moves away from it, it changes its direction. So naturally, when we saw this or preliminary testings, the amount of electricity that was occurring, it was creating an AC current. So in order to bring that into applications for DC generation, or in a sense to charge a battery, we decided to connect it to a bridge rectifier to be able to then store it and have that ability that we need to harness that energy and bring back to the system, just in the case of an automobile. And so this is, in a sense, we see we had to use coils and magnets, and the coils that we produced were actually custom fabricated in order to fit our design. Our design had a specific length of like 5 inches, and we chose a specific amount of turns that would bring an optimal amount of voltages for each coil. For each of the coils that were used were about like 500 turns each. And so from these, and we also decided to choose a thin copper wire in order to bring the most density into it. Because the more turns we have, the more we have the ability of causing a stronger current out of this application. And through all these ideas, our preliminary designs actually showed success in bringing energy, as we'll see in further testing. For the design of the actual turbine, we planned on changing it a bit, as we saw that in the initial white models, we're not producing enough of the torque that we needed to generate some revolution, enough revolutions to be able to produce magnetic induction. And so one of the second types of blades we call the second generations were turbine A and B. As you see here, there's two different sets. With the bearing that we had at the time, we chose to open up the airflow of the, or the diameter of the duct as a conical shape, in a sense acting like a diffuser. If you notice from the inlet in turbine A and the outlet, the diameter increases in order to kind of satisfy the dimensions of the bearing. For the difference between turbine A and turbine B is that initially we thought if we increase the blade distances going from 0, as seen in the inlet in turbine A, all the way extending down to the outlet, we'll be able to gradually transfer the power of the flow without not causing too much excessive back pressure, which we're trying to avoid to bring back into the system. Another option we had that we tested was turbine B. If we were to just initially have the blades extend out from the beginning to the end, and then from there we could test how much of back pressure would increase in that manner. And so these are just some of the preliminary testings that we were producing. Initially we were just holding the device from an airflow that was coming out of the apparatus in order to see how well the actual spinning effect was occurring. From some of this on the left is a turbine A, which had the blades not sticking out in the very beginning. And this right here in the right side is turbine B, which was actually spinning a lot faster. And from rough estimation, the pressure difference wasn't that much. But because of these two big preliminary testing, we noticed that even then the spinning wasn't fast enough that we needed to use. So we had to change the actual model. We actually came down and analyzed what was the results, why was it not spinning fast enough. Came down to the conclusion that the components that we're using, such as the bearing, were causing some resistance. And these were the results of the pressure that we found there.
And we can see that the pressure difference was quite significant with these first initial turbines. The blue line on the left represents the free-flowing pressure along the system. Green line represents turbine B, which is the turbine with the small blades in the beginning. And the red line is for turbine A, which has initially a 0 blade height. And we can see we have 110% pressure increase with turbine A. That's not acceptable. So we figured we have to change the design completely. So instead of having the pipe coming in with the bearing around the pipe and the turbine outside of the bearing, we'll go with a bearing that will fit inside of a larger pipe. So here we have a thin profile bearing with an outside diameter of 3.5 inches. So we're looking at a large truck exhaust pipe. And the weight difference is much greater, 90 grams versus 155 grams. So we're spinning a lot lighter of a bearing. This is the new turbine design. We just threw something together to see if the thin profile bearing would work. So we did just a rough sketch, not intended to be a final design. So we just put it up and put it in front of the pipe, and then this happened. So we can see it's spinning much faster than we even expected. So we knew that coming from using the thin profile bearing, this is the direction we want to follow. So now we need to optimize the blade within the turbine, and optimize for the magnets that we have and all that.
For the final design, since after the testing we was able to come out with a successful amount of revolutions that we needed, we finished the modeling and be able, instead of having the slots that we noticed in the other model, put on the outside where the magnets would be placed, we decided to actually put it embedded into the thickness of the walls of the actual turbine in order for the magnets to be easily placed and assembled. In this matter, this is the complete version where this will actually be a cap taken out where magnets are being placed into the slots so that they will be in close proximity with the coils. And so we did some final simulation, flow simulations in SOLIDWORKS, and seeing the final design we were going to test, we noticed that we were looking mainly for any areas that would cause any blockages in the airflow. And for most of the pressure distribution, we noticed that the area was able, the heatable design was able to not cause so much of a pressure difference, which we then, from this point on, we continue to go on with final testing. Another important aspect was we needed to design a coupler that would properly connect the housing for the coils as well as for the bearings and the turbines, and kind of created a multi-system that was all placed connected directly to the apparatus. And so this is the current model we have with all the assembly connected together. The clear tube was just for visual effects so that we can continue in the experiment seeing the turbine spin. the coils would be placed on the outside. We chose 6 spokes, as you've seen in later models, in order to produce the amount of current that we needed. And this is the final assembly that we have in full with the coils and with the turbine included. One important aspect, we needed to position the coils in the proper degrees, just like the spokes were evenly, so that each of the magnets would all hit the coil simultaneously and be able to produce the current that we needed. And so this is the final turbine experiments that we did, measuring the voltages for different flow rates. We're producing about an average like 2 volts. The tape right there is just for visual effects in order to see the revolution of the spin. Some of the initial results we were able to get about like 50 milliamps of power out of that. And this is one of the final testings we did without any disturbances. We actually put a load onto the system, as such as an LED. And we were able to calculate that at a high enough voltage was able to pull out well enough power for us to show that there was an application for this. So these are the results of the electrical power that we were able to pull out. One of the key things we did was, in the beginning, we decided to test in what configuration we needed the coils to be in series or parallel, and the experiment came out that in series, the power wattage was coming out a lot greater. So from that, when we used all the coils put into series, we came to see what was the maximum power that this system was actually producing. And it came to about 533 milliwatts in one of the optimal speeds magnets, which so far was an energy that could be pulled out. And then later we were able to calculate what was the back pressure that was causing the conclusion of the turbine.
Right, so we're able to calculate that, or determine that we can capture voltage and amperage, but do we know if the flow coming out of this apparatus is even meaningful? So the chart on the left shows different engine sizes and different engine speeds, calculating the amount of volume flow that we've got. Because we're using air for our testing, the results are not exactly spot on, but we've got a general idea of the type of flow we've got. So even for a typical 5-liter engine at cruising speeds of 2,000 or 3,000 RPM, we've got 80 to 100 liters per second. So to compare that to our testing flow rates, we've got the different speeds we've used on the apparatus. Using the pitot tube, we were able to calculate the velocity of flow coming through, and then of course with the cross-sectional area, we're able to determine we've got between 60 and 70 liters per second. So our flow rates for testing are fairly comparable to expected flow rates from commercial trucks.
So as far as our back pressure results, this is the apparatus, the final design set up on a vertical pipe. We wanted to simulate vertical because we meant it for trucks. Trucks usually have a big vertical pipe on the tip. And this right here is the measuring of the pressure right at this before the turbine and then after the turbine. And here we can see that there's an average of 9.6 increase of back pressure for adding the turbine to the whole system. Now this is at the tip. Further tests will have to be done and see if that transfers back to the engine as far as if it's going to cause any inefficiency. This was our timeline. We spent a lot of time testing and initial testing. As far as for testing, we took each one of those measurements 5 times for all the different speeds in order to have a more accurate result, and then we did the same thing for the turbine. Cost. Our total cost came up to be $955. Actually, one of the most expensive things were the bearings. The single bearing that we used was like $53. Sorry. Well, it's an $82 because that's accounting for the 2 smaller ones, but the bigger bearing was $53. And then the use of the 3D printer was very helpful for our project. Thank you.
Questions?
I like the project.
Well, first, thank you.
But the questions I have is some is on the bearings and the fact that you're going to be putting this into a truck that's going to be running 24/7,
Right.
extensive, are those bearings going to survive? Is that the right design bearing for the application?
We went with ultra thin. We have to figure out which bearing would be optimal for, especially the temperatures and the revolutions per minute.
Exactly, because you've got cold, they're going to be in
Right.
sub-frigid temperatures plus real warm temperatures.
Right. The highest temperature that particular bearing used, according to the manufacturer's website, was either between 140 and 175 degrees Celsius, which is not really that high for our purposes. So
And lubricating the bearing.
lubricating is the biggest issue because that's what diminishes the temperature that it could withstand and the friction as well. The bearing itself is made of steel, so.
Is there a reason why you don't have two bearings?
We originally thought of two bearings, but I thought for testing, we would have to create a whole other pipe and then put the two bearings. Because we don't want to be holding it, we want it to be self-sufficient, not self-sufficient, but self-applied, so we didn't have to, there was no human error, that's why we built the couplers. But yes, two bearings would definitely increase the spin.
Okay, or a bearing and bushing, maybe.
Yeah.
So these tests are necessary. The other thing is magnetic field through an exhaust pipe. Because I see you're doing it in plastic. What's it going to look like if I have a nice piece of carbon steel sitting there?
Well, this wouldn't be through the exhaust pipe, this would be really an apparatus attached to the end or in line. So we would have the turbine itself be made of aluminum or some other non-conductive material, but the casing would still be something that's not conductive.
But it would be able to resist the temperatures.
Has to resist the temperature.
Yeah, our biggest issue with was not being able to test temperatures within our labs or not sit behind a car and take temperatures.
And then really the last question is all about the materials in the final system, because obviously the plastic that you're using for that turbine isn't going to survive.
Right. Funny story. If you leave this in your car with magnets, it will work. That's this guy.
It will.
It will work.
It actually works.
So this one was our second prototype.
But mainly the focus of our experiment was to actually measure the flow areas without the temperature, to see if it was even plausible to flow energy out. From this, we can actually continue on and be able to produce an actual fabrication of metals that will resist the temperatures.
And the magnets we use, the neodymium, they range from 360 up to 800 depending on the chemical properties that they use to combine. And we didn't have to use any type of glue for the magnets. We just use opposite polarity slide them in, and the cap keeps it in place. So there's no glue that would melt or anything.
Easy as that.
You said that there were some challenges measuring the temperature of the lab. Explain that to me.
Well, temperatures like for the car at the end of the tailpipe,
Yes.
it'll be 200, even higher. So like I don't want to be trying to put this on top of at the tip of a 200-degree piece.
Mainly, we didn't want to actually use this plastic to put into a real car application because it wouldn't have resistance. So that's why we use an apparatus in order to just simulate the flow. Later, we'll be able to design the proper right material we'll be able to use to put into an actual application.
All our flow calculations are ambient temperature, 20 degrees Celsius. So the temperature actually will affect the velocity ratings due to the density. And you also don't have just air coming out, it's carbon monoxide and different things which have different densities, which will adjust the velocity coming out. So just not dealing with those gases didn't provide us further research there.
I had a couple questions. So you did some simulations to try to figure out back pressure. Did you try to look at the pressure on each one of the turbine blades and use that to maybe design the actual blade system itself?
We didn't do too much design into the blade itself, the whole science just behind that. So we just kind of use a flat profile along the length of it, but there's obviously the
Other opportunity.
Yeah.
It's like a whole field of study actually you can do to perfect what we've made.
So far, the testing have shown to be pretty reliable.
Are you done?
Sure.
My final question, has anything like this been done before? Seen in the lit review? anything
No,
like this?
Not that we could find.
We're actually
I was about to say no.
No?
should we mention?
You mentioned, go ahead.
Yeah? No, we will probably file for the invention form through FIU.
Okay.
Try to get a patent. That adds value, well, to the university as far as having patents and us, I guess.
And before someone steals the idea. Someone in there steal this idea?
I have my printer running right now.
Any other questions?
Put in a notebook and sign it with a witness.
All right, no other questions. Thank you so much.